morning and welcome to SingularityNET's renewed Technical Tuesday discussions. I'm Hayley Lowey, the Alignment and Coordination Officer for SingularityNET, and I'm joined today, so thrilled to be joined today, by Alexey Potapov, our Chief AGI Officer, and Vita Potapova, our Hyperon Project Manager. Of course, along with these roles, you are both amazing researchers into AGI, helping us build and develop the Hyperon project and the meta language and other components. And I want to dive in today with both of you on a paper that you presented at the AGI 25 conference. You can highlight in a few words the direction that this paper was looking to peer into.
If for me this paper was an attempt to be honest with myself and to not just criticize LLMs, but to really try to understand if we need to follow this path somehow, or it's really the case that they are not enough. And I was trying to do this very carefully to convince myself and maybe others, but myself in the first place, that in fact, LLMs are still not AGI, and they cannot be a central component of AGI in their current form.
I think the paper was a brilliant exploration of that. You really dove into all the different possibilities that seem apparent for how they could be AGI, or what they would need to be AGI, or possibly useful to AGI. Perhaps you can each start by talking a little bit about some of the problems that LLMs are currently displaying, some of the issues with LLMs that demonstrate they are not in fact AGI currently. You outlined them so well. And I think that that's the perfect starting place to show why we're looking in this direction to people who may not understand what we're pointing at with AGI that's not simply more stronger LLMs.
Well, first of all, the well-known problem with hallucinations, they are not reliable enough to help people with some other stuff where there should be precise understanding of the topic. They're weak in reasoning. We cannot, again, rely on what conclusions they make.
The main idea behind the paper was not just to talk about well-known practical limitations, because they are well-known, but I would frame it in terms of memory, because LLMs don't have internal states, and they typically do not perform online learning. So you need to provide some additional lifetime or runtime information via prompts and so on. You can mitigate all these limitations by different means, like chains of thought and so on, by using retrieval augmented generation. But these limitations are caused by some deep architectural flaws, and they cannot be fixed by just augmenting LLMs with external tools, as everyone is trying to do.
Absolutely. Thank you so much for that outline. That's a great one. The internal state component is something I want to dive into. I think that it's so important, this aspect of memory. And as somebody was presenting at AGI 25, the problem with LLMs and Tic-Tac-Toe, even, as a very simple example, you know, a 3 to 5 year old will already begin to grow bored with Tic-Tac-Toe because they understand, you know, how to win very early on. It's very deterministic. But an LLM can tell you all about how to win Tic-Tac-Toe and the exact algorithm to take, and you can present it with a board where it's got one or two moves to win, and it will still make the wrong move, right? It doesn't have that memory, that internal state, that understanding of how to apply all the language it knows to solving even a very basic problem that a 5-year-old is bored with. Can you speak just a little bit more about that internal state, the working memory, and how LLMs would need that, or perhaps could be augmented with that in a way that would elevate their intelligence towards something more like AGI?
So basically, they use this prompt as a working memory. And the issue with this is that a representation in this working memory is also textual. It's actually not bad, because texts can describe nearly everything, but still this representation is not well structured, and when LLMs encounter a really novel task, it's impossible to avoid enumeration of different possibilities, because if this is an NP-complete problem, then there is no other way but just to enumerate at least some possibilities with pruning search tree with heuristics, or performing some sort of genetic algorithms or whatever. In any case, you need to enumerate different candidate solutions and to evaluate them. And it's quite difficult to put all these candidate solutions back into the prompt and to see that this part of a search space has already been visited, and we do not need to revisit it to structure how we perform this enumeration, to keep partial solutions if these solutions are somehow growing, and so on. So in really novel tasks, reasoning or combinatorial tasks, when you don't have examples in training set which were memorized, and you can just recall or interpolate between solutions, you have to do this sort of heavy search, be it reasoning or whatever, but you do need to perform this search. And LLMs, well, you can try training them not with just a chain of thoughts, instructive pre-training and so on, but with enumerating different candidate solutions, but it looks unrealistic. For example, if we imagine LLM playing Go, then will it keep this huge amount of boards and positions in the prompt? I guess no. So using prompts as a working memory has a very hard limitation, because its size is limited, and the way how you represent information about your progress in solving the task is also limited and not very well suited.
Interesting too, because it doesn't work well as a working memory. You've got a prompt. It's not designed to be memory. It's designed to be a prompt.
Exactly. We need memory, and it should be both working memory and long-term memory. And LLMs would be more effective if they would have internal memory. But in their current form, it is impossible.
So interesting. And I think one of the almost the closest thing that people are doing to try and address this is the graph rec, but that's not even memory. That's just symbolic knowledge. I think that it might be even more poignant to talk about reasoning. You talked about how they're very weak on reasoning. LLMs are very weak on reasoning, and this is something that having LLMs at the center is always going to be problematic for solving real world problems.
Well, it's a little bit dangerous to say that they are very weak at reasoning because they can outperform humans at reasoning tasks when these reasoning tasks mm, standard tasks. So when you kind of have similar or even the same tasks in your data set. But indeed, if we consider this with finer details, then yeah, it's sometimes very funny how weak they can be. I personally quite frequently feed them with Olympic math problems for elementary school, which are quite simple, and it's quite often that they cannot solve such problems. But with advancing of LLMs, they are becoming better and better at this, but still there are too many problems they cannot solve. Even they can pass exams to universities or whatever, but if a task is a little bit non-standard, then they fail.
And you've identified some of these critical failures that LLMs have. First, the handling of large volumes of novel information, and then solving genuinely new problems in this way. Sam Altman, I believe, recently suggested that Turing 2, the new Turing test, should be the first AI to solve quantum gravity will be AGI, which, besides completely missing the point of generality, also is trying to get LLMs to solve a genuinely new problem. So can you speak a little bit towards why LLMs have that difficulty, and what we might be able to do with LLMs or alongside LLMs, or if they can be helpful in building an AGI that has this type of capability?
Actually, this is maybe the most important internal limitation of LLMs because it follows from how they work, how they learn. Uh, they are bottom-up information processors. Of course, we can add some loops like chain of thoughts. Again, it blurs, unfortunately, the analysis. But in any case, what LLMs are trained to do is to predict next token based on the current prompt. And actually, it's not bad in terms of AGI because, say, IXC model or Solomonov induction are doing kind of the same thing. So we have a history and we condition our predictions on this history, and this is one of the core components of AGI, of what intelligence should do. But the question is how it is done. LLMs approximate these predictions based on predefined transformations. Well, everything actually is quite complicated.
I like your analogy with the term skills, that LLMs are pre-trained skills, and that doesn't sound complicated.
Of course, once again, we go back to NP-complete problems as an example. Then it should be obvious that LLMs cannot solve novel NP-complete problems in one pass because they perform a fixed amount of computations. And what they can do is to construct a sort of hash of solutions in a very interesting but still restricted way. So they can memorize these solutions in a specific way, which can be used to interpolate between them and so on. But since they perform a fixed number of steps, they cannot represent solutions to these problems as specific algorithms, as specific regularities. Say, if we have a exponential curve and we are trying to approximate it with polynomials, then we can do this in a certain range of values, but when we go outside, they will diverge very fastly. This means that we cannot represent an exponential function in a different way, but to use this exponential function. And the space of algorithms provide us with all possible regularities. And what LLMs are doing, they are trying just to approximate these regularities with a fixed set of functions. And they do not represent these regularities, they do not extract them. It can be not precisely true when we are talking about language, because they can write different programs which represent algorithms, but they cannot execute these programs. So this is a sort of paradox, because they can write a program which they cannot execute. So how it can be possible? They cannot really fully understand the mechanics. They cannot have an internal representation of a Turing machine inside themselves. They can well, they can emulate a Turing machine, possibly to a certain degree, using this chain of thought cycle when they feed themselves with the output. But the larger the result of the algorithm will be the worse the next prediction will be. So because of this tricky way of how LLMs are working with memory, it's difficult to pose absolutely certain constraints on them, but still they will not do like millions of reasoning steps to achieve something. They are working in a different way. And here I would like to make an analogy with AlphaGo, because it also works in a bottom-up manner, and it hashes a lot of games. It plays like hundreds of millions of games are hashed in its weights, and it plays very efficiently, because it learned all these possibilities during the training process. And actually, if we would ask whether AlphaGo is thinking, it is thinking during training, because it enumerates different possibilities, and you can consider this as a preliminary reasoning about everything possible. And when at inference time it doesn't think, it indeed plays as an instinct, as a reflex, as a sort of skill. So it's a trained skill, and LLMs are working in the same way. The one pass is similar to one pass of AlphaGo. So it's just producing something by reflex. So we have something in input. Okay, this should be as output. Of course, there are some questions whether our intelligence works in a similar way. Maybe, and actually, it is in certain sense because our higher levels of cognition, they are built on top of reflexes and instincts or whatever. So there is a hierarchy of control systems which control more and more layers beyond them. But there is, and we can actually try to build on top of LLMs, trying to control them, but there are other differences between LLMs and our intelligence.
Absolutely, yeah. They can look so intelligent to us because we, many of us, embody on a day-to-day basis this linguistic reflex that you mentioned in this sort of skill, automated. But we have the ability to also deep think about new and creative problems, solutions, art, creation. Thank you very much. I really like that analogy of being the skill training and anything that is not already pre-trained somewhere as a skill, an LLM can't learn or execute in real time. And if discovering quantum gravity isn't a skill, isn't a math Olympia that has a lot of training data, then LLMs as they are aren't going to get there. I had one more question on the paper, and then we'll wrap up with a few thoughts. But you mentioned in there that it might be possible to move LLMs to become a true generative model. Can you speak more to what a true generative model, what you mean by LLMs becoming true generative models would mean?
Currently doing is predicting. So they're just predicting the next token. And a natural direction is to make them truly generative. This would mean training transformers to first build a latent representation from the entire prompt, including its own reasoning. And this can be reconstructed.
Well, yeah. So basically, as Vita said, when we consider only next prediction, it's a conditional model which doesn't produce the whole prompt. Even if we condition it on some given prompt, it still generates only one token. And the whole generative model should assign probabilities to the whole text it should generate and actually to the prompt which was given as well. And LLMs as next token predictors are wrapped into some chainer which takes the next token, puts again to the LLM for it to produce next and next token auto-generatively, auto-regressively. But in this process, they do not produce, if we just do this in this way, token by token, then the result will not have the highest possible posterior probability because it's like moves in chess. We can make moves which look locally the best moves, but then we can find ourselves in an impasse and all the moves become bad. So we need to once even in this case we need to consider different routes of how to generate tokens and select the most overall probable sequence. And there are different ways of how to do this. Beam search is typically used, so LLMs are not just generating one token and it's selected, fixed, and they generate the next token, selected and fixed. No, they support several sequences of tokens, and they are trying, not LLMs, but wrappers of LLMs. They are trying to keep a number of such predicted sequences and to select most probable sequences. And there are also other approaches like energy-based transformers, which try to optimize the probability of all the generated tokens and possibly previous tokens if it is needed by additional gradient descent, because we have generated some sequence and we can and we can calculate the total energy or total posterior probability by the chain rule, and we can take a gradient of it, and in this case, if we are working with energy to do descent, if we were working with probability to go up hills, and they will try to optimize each token in such a way that the total probability or full energy will be optimized. But even in if we do this, it will not give us a latent representation of the prompt. So it will still be an autoregressive model when we condition each next token on previous tokens without any, well, not precisely any internal representation, because there is some internal representation at different levels of transformers, but no one knows what part of this representation to take, and so on. So transformers are actually similar to autoencoders, but with shifted reconstruction. So you do not reconstruct the prompt, but you reconstruct the prompt shifted by one token, basically. But in autoencoders, there is a layer of the latent code from which you can generate your inputs. But in the case of transformers, there is no such a layer. There is no representation of this input and output with which we could work. And this actually makes it difficult for transformers to have states besides the prompt itself. If key had such an internal representation, then it could be a memory state, and it could be updated during reasoning and so on. So instead of applying a chain of thought, this internal state in internal representation could maintain our, or not our, LLMs tokens imagination or just a representation of the current state of its reasoning.
So we're coming to training LLM-based AGI model. And this would be more complex than training standard next token prediction model.
easy to begin from the perspective and the knowledge and the research that we've done into AGI. It's very easy for us to point at, as Alexey said, the issues with LLMs and how they are not currently AGI and where they fall short of heading towards AGI. But I think your paper was also sort of hopeful. There are directions that we can go that could use or utilize the skills of LLMs or augment or build on and be more toward AGI-ish. Could you speak more toward those directions? How can LLMs be augmented or utilized in AGI-ish systems in ways that look hopeful and advancing the technology?
Augmenting LLMs with additional tools is not a good way towards AGI. So we can mitigate some current limitations of LLMs and improve them in practical tasks to a certain extent. But the further we go with trying to mitigate these limitations, the farther we go from LLMs to something different, to basically cognitive architectures, be them purely neural or neural symbolic cognitive architectures, but still, if we add some internal representation into LLMs, some working and long-term memory, some reasoning internal loops like in recurrent networks or something like this. They will not be LLMs, and the more we do such modifications, the more and more difficult it becomes to train such models, and that's why LLMs are good, but they are good as what they are doing. So they are good as language reflexes, and it's not like maybe it's not like we need to modify LLMs or augment them, but just to use them in what they are good at, basically at providing solutions to repetitive tasks, to serve like language skill or reflex or instinct or subconscious, some subconscious substrate or whatever. But how to either to build on top of LLMs or to use them as a side component of other AGI systems, it's really a separate topic for discussion.
And what LLMs taught us is that AGI is no longer a scientific pursuit. It is an engineering problem. Only scientific, but yeah.
Because it's still scientific.
Yeah.
Fantastic. I would like to dive into that more on our next episode. Thank you very much for joining us here today, and talking on all these aspects. It's such an education. It's such a privilege to be able to hear from you both on the topic of LLMs and AGI, and the distinctions between what we're currently seeing that has just overtaken the world, and what could happen. What could be with a future of AGI-ish systems that go beyond what LLMs are capable of. So thank you very much.
Thank you.
Thank you.